morning, everyone.
Good morning.
Great day before Thanksgiving, huh?
Yeah, hard to believe it's already here.
I know. Is this week 14? Do we only have 2 weeks left after this?
I believe, yeah, it
Oh
looks
my
like
goodness. Where'd the whole semester go? It's really weird because about midway through the semester, I look at my calendar and I go, wow, we're about a week ahead, or at least a day ahead. And then somewhere we lose that. And then we run out of time. Because we kind of like, I mean, we got a couple of optional things to do, but we also, in this class, have to have the quick little conferences with me over Zoom over the next 2 weeks probably to look at all the work that you've done. I need to also catch up on all the feedback and stuff on the assignments. And then, figure out ultimately, what grade you're going to get in the class. So I have to work on how to schedule all those things in over the next couple weeks. I'll have to work on that this weekend, figure out some way to have some kind of sign-up sheet or something, sign-up page where you can sign up for a slot. But since it is the day before Thanksgiving and we probably have stuff to do, or at least I do, why don't we dive right in and see how far we get today. So last time I left you off with this diagram. This was NFAs with epsilon transitions. So there's a way to go straight through, or you could skip over the X, or you could go through the X and go through the Y and then jump back and maybe do a Y again. Whole point is to get to this accepting state, but there's many different ways to do it. Why don't we start with trying to figure out what would be a regular expression that accepts the same strings. So we know that you can either do the X or you can skip over the X, but there's only one of them at most. So that makes the X optional. We could do it two ways. We could say X or nothing. Alternatively, we could use the extended regular expression symbol X question mark. And then what do we do with this Y and the epsilon coming back?
I had a question about this when you drew this last week. Can this end up on an accepting state? Because if we do the Y, it takes us to 3, but then doing nothing brings us back to 2. So is there a way to signal that we're finished?
I mean, the goal is to get to this accepting state, right? So if you do a Y, you can just end up there, or if there's further symbols to do, you could then jump back and do this. So you don't have to take the epsilon transition, but it's one of your options. Does that help?
Yeah.
Okay. So we've got an optional X, and then what do we do with the Y's? How many do we need at minimum?
Just one.
Just one, right? But we have to do one. We can't skip the Y's at all. So we have to do a Y, and then we could loop back and do more Y's. So that's kind of like a loop, right? So as a basic regular expression, we can do X or nothing, followed by a Y, and then 0 or more Y's. For an extended regular expression, we can do an optional X, followed by 1 or more Y's. So let's try to transform this into a deterministic finite state automaton. So what's going to happen is all these epsilons are eventually going to go away. So we're going to do that the same way we did the transformation last time, but now we have these epsilons to deal with. So we're going to start in state number 1. And actually, we're not really going to start in state number 1. Let me erase that. So we're going to enter into this room, and we can either stay here, or we can jump ahead to number 2. So really, our starting state is either state 1 or state 2. So if we're in both state 1 and state 2, and we ask what doors do we see leading out, well, if we were in 1, we see an X, and if we're in 2, we see a Y. So we know that there's an X and a Y. If we take the X door, it leads us down to just 2. So that's a new state. And if we were in room 2, and we take the Y door, where does it go? Where do you think it goes? So if we walk down this corridor, we'll end up in 3, and because of the epsilon, we'll also potentially end up in 2. So that's also a new state. All right, so if we walk down the Y, we end up in 3, and because of the epsilon, we also potentially end up in 2. So there's 2 possible places we could go if we walk down that Y corridor. Now let's turn our attention to the 2 here. So if we are just in state number 2, what do we see? Well, we see a Y, and that's it. And the Y leads us to 3, and also potentially back to 2. So if we're in 2, and we see the Y, we'll end up in 3 or 2. So that means there is a transition like this. And then finally, if we are in 2 or 3, so if we're in both of these simultaneously, we see only a Y. We don't count this one here. There's no door actually labeled epsilon. It's like a door with no label. So we see a Y door, and that's it. And that Y door takes us to 3, and also potentially back to 2. So that means this loops back on itself. All right, anything with a 3 is an accepting state. All right, so you look at all the accepting states in your NFA, and any state with those numbers in it also become accepting states. All right, let's see if it works. So we've got an optional X followed by 1 or more Y's. So we can do X followed by a Y. We can do X followed by a bunch of Y's. We can do no X with just a single Y. And we can do no X with multiple Y's. Okay, so let's try that again. Here's our NFA, and we know it's an NFA because, well, there's 2 reasons it's an NFA. One is you've got 2 A's here, you got 2 B's here, so there's already some ambiguous transitions, and there's also an epsilon. So we'll start out the same way. what's our starting state? Well, if we enter into room 1, that's as far as we can go. We'd have to walk through one of these labeled doors. So we know that our starting state is 1. And sitting here in 1, there's an A and an A leading out. So there's a single A leading out in our DFA, and it goes to 2 and 3. So now this one is done. Let's turn our attention to 2 and 3. So looking up here, if we are in 2 and 3, I see a B leading out, I see a B leading out, and I see a B leading out. So there's only a single B leading out. But that B goes to 4, 2, and also 4. And also, anytime we end up at 4, we can also potentially end up back at 2 again because of this epsilon. Okay, so if we follow this B, we can end up at 4, and we can end up at 2. If we follow this B, we end up at 2. And if we follow this B, we end up at 4 and potentially back at 2 again. So our state on a B is 2, 3, 4.
Why is it?
Yeah, why 3?
Because I'm not paying attention. Let me try that again here. So this B goes to 4, takes us back to 2, this goes to 2. You're right. Yeah, I'm not paying attention. Let's try that again. 2 and 4. Computers are so much better at this than I am. Okay, so out of 2 and 3, there are no A's, so we're now done with this one. Two and 4. So if we are in here and here, I see an A going out, and I see a B going out. So where does 2 and 4 take us? What would be the next state on an A? It would be 3. All right, we'd follow the A, come back to 3, and then that's it. And if we follow a B out of 2 and 4, I think there's only one B to do, that's this one here. That takes us to 4, and then the epsilon takes us back to 2. So if we follow this B, we could end up in 4, and we could also end up in 2. So that means this loops back on itself. For 3, there's only B's leading out. This B takes us to 2. This B takes us to 4. And the epsilon takes us back to 2. So that means on a B out of 3, takes us to 2 and 4. And then this one is done. So that's it. We've fully explored the map. So this should be our DFA. Oh, last thing to do is mark our acceptings. So anything with a 3, so this one here is an accepting, so anything with a 3 becomes an accepting. Okay, that should do it. So before I go further, I addressed this last time, but I'll do it again. Why do we have these epsilons in here? Well, there's two reasons. One is it allows us to make finite state machines that have these transitions that you can either follow or not follow. But ultimately, the reason why we can have them there, a good practical reason, is to allow us to do regular expressions like this. This is either A or B star. And if we try to draw it kind of the naive way, we got A, then accepting, and then our loop on B. But the problem with this regular expression, and this finite state machine is the two of them don't accept the same strings. This one accepts either an A, or it accepts nothing, or any number of B's, but not a mixture of both. However, this state machine allows us to mix them. We can do a bunch of B's and then do an A, which this regular expression does not allow. So we resolve that kind of manually by doing something like this. We had a B and then a loop on this one. And then we ended up making this an accepting, this an accepting, and this an accepting. So now you can do nothing, or you can do a single B, or you can do a bunch of B's. But once you decide to go down this branch, you can't return back and go do more A's. So this works, but it took a little bit of kind of thought and analysis in order to come up with that solution. If we had a more complex regular expression, then this diagram would get a lot more complex. So what the epsilons allow us to do is kind of isolate different branches of our finite state machine. We could do something like this. Here's our starting state. We could do our A here to go to accepting, or we could do an epsilon here and then do a B with a loop. So we could either go on the A and end up in our accepting, or we could take this epsilon and then end up in the loop for B's. Once we take this branch, this lower branch, we can't turn around and go back and do any A's. We could even take it a step further and totally isolate the A branch and the B branch from each other. Like this. So you're sitting here in this start state, and you can either go on this branch and do an A, or you can go down this branch and do a B. So from a practical point of view, the epsilons can allow us to isolate different parts of the state machine so that we can't go back and do other parts of the state machine if we're not supposed to. So that forms the basis for what are called Thompson's constructions. And these are actually a slight modification from what you might find on the internet. These are a little bit simpler. What you'll find on the internet has more epsilons in it, but this will work for our purposes in this particular course. So if you have a sequence of symbols or regular expressions, then you just line them up, right? That's the same as we've been doing before. If you have an or, then you do branches like this. And then the one that's really different is the star. So I call this the UFO operation because it kind of looks like a flying saucer. It's got a whole bunch of epsilons in it. And then there's our single symbol in the middle. So as you can see, you can do no A's if you just skip over entirely. You can do a single A if you go through using the other branch. And then you can do multiple A's by coming down this branch and then looping back. But notice that through the use of the epsilons here, we've isolated those two branches. We've also isolated the exit out of this to make sure that you can't go back and do another A. Like if these epsilons came to here instead, and this was our accepting, so we forgot about this, right? Then that will give us the opportunity to come through and then loop back and do some more A's, right? So we've isolated the entrance into the loop, and we've isolated the exit out of the loop to make sure that once you decide to do some looping, that's all you do. Okay, so the sequencing looks pretty much the same. Alternation looks pretty much the same. It's the star that looks different. So let's see how to apply those to a regular expression and turn it into an NFA. So here's our regular expression. So the first thing I do is I look at the expression and I see, is it possible for me to break this up into some larger pieces? And what I see is an X, and then this Y or Z star, and then just a Y. So I see three pieces here that are actually sequenced together. So I'll do this kind of step by step. You apply one set of Thompson's constructions, and then you try to break down each one of those into smaller and smaller pieces until you arrive at most one symbol per transition. So the first step I'm going to do is start, then an X, and then here I'm going to cram in Y or Z star, and I'll work on that later. And then finally a Y with an accepting. So I've got an X followed by a Y or Z star followed by a Y. So that's a sequence of three smaller regular expressions. Each one of these is a regular expression. This is a regular expression, the middle piece is a regular expression, and the Y alone is also a regular expression. So I've got one symbol here and here. I just need to work on this central piece. So the central piece, I'm going to use that UFO shape. I'm going to expand this out into that UFO. So what I'm going to do is I'm going to kind of leave as blue the stuff that I'm not changing. And then here is where I have this new piece. And then my Y doesn't change either. So here's my UFO. Epsilon here, epsilon on the end. In the middle, I'm going to put Y or Z. So I'm not going to worry about breaking this down just yet. I'm just worried about handling the star. I've got an epsilon that skips all the way over to the end, and then one that does this loop back in the middle. Okay, and now let me handle this Y or Z. So I've got the X here, using all these different colors to illustrate the different parts of this Thompson's construction. Okay, so that's it. That's the whole thing. Now I've arrived at just one symbol per transition, and so I'm done. Okay, so I started out with a sequence of 3 regular expressions, and I wrote it out as a sequence of 3, and then I replaced this center section with this new construction here. And then out of that, I replaced its center section with this one. So it's a sequence of, sequence of successively replacing chunks of the finite state machine until you arrive at one symbol per transition. The nice thing about this, even though this star operator is kind of complex, is you don't really have to think about it a whole lot. All you have to do is think about the order of operations. In this regular expression, the thing you do first, or the thing you do last, is to sequence these pieces together. And then within each one of those pieces, you can further break it down into smaller pieces. So you're really just looking at the regular expression and then looking at your Thompson's constructions and seeing what can I just fit in there, pretty much without a whole lot of thought. And this is great for computers because computers can just look at a regular expression and then figure out, okay, I see a sequence of things, so I'm just going to line that up as a sequence of states. And I see an alternation here, so I'm going to replace it with 2 branches. And I see a star here, so I'm going to replace that with that UFO construction. So you just kind of thoughtlessly apply these constructions to your regular expression, and then you arrive at an NFA that works. It is complex. It does have a lot of states and a lot of transitions, but it does work. Then you can go through the process of converting that NFA to a DFA, and then you'll finally arrive at fewer states, hopefully, because a lot of those epsilons will disappear, and then you can also implement that DFA as that loop with a bunch of conditionals that I showed you a couple weeks ago. So this really is the process of compiling a regular expression into a DFA, which you can then turn into one of those dictionaries with an engine that I showed you. So this is really a compilation process. You are breaking it up into its individual tokens, so you're doing the lexing and the tokenizing, and then you basically have to break it up into a tree, and at the very top of the tree is the last operation you do. At the bottom of the tree are your symbols. And then that leads you to your Thompson's constructions. Then you walk through a process of transforming your Thompson's construction into a table, and then from there an NFA table, and then from there a DFA table, and then from there you got your finite state machine that you can implement on a computer. So you're going from regular expression to loops with a bunch of conditionals. And that's a compilation, right? You turn one language, the language of regular expressions, into another language, like Python or Java or something like that. Okay, so let's try a couple more. This is old buddy, you know this guy, this is Omnom, right? From that old game Cut the Rope. Well, let's see if we can transform this one here, number 1, into an NFA using the Thompson's construction. So we'll start out with, let's see, what do I see? I see here something on the left, this big chunk on the left, and then this big chunk on the right with an OR between them. So I'm going to draw that as just two states. And on the top is A star B, and on the bottom is A. And then within A star B, I can break that up into two pieces, A star followed by a B. So I will replace that with an intermediate state. Here's my A star and B, and then A on the bottom. And then finally I'm going to replace this A star with that UFO construction. Here's my B. In the middle is the A, then an epsilon here, epsilon here, epsilon there, one going all the way, almost all the way across, and then finally my A at the bottom. Notice that I didn't put a whole lot of thought into it. The only thing I had to do was just figure out what's my order of operations. Once I did that, I just applied the Thompson constructions without thinking about it too much, and I arrived at this fairly complex NFA, but it'll work. And then for number 2 over here, I see kind of like two pieces. I see OM and then NOM star. And I know I can break up this OM right away. So I'm pretty sure I can handle that. That's O, followed by M, followed by NOM star. And then I will break up NOM star into that UFO. O, M, epsilon, NOM, epsilon, and then put in my loops. And then finally I can break up this NOM into its 3 little pieces. And there we go. So we can do OM and then skip over to the end, or we can do OM, NOM, and then come back and do NOM, NOM, NOM. All right, any questions so far?
What's the order of operations? So like, for example, on number 1, when I looked at it, I thought it was A star and then B or A.
Yeah, so that's not correct, because OR is kind of like plus. And sequencing is kind of like multiply. And then star is kind of like exponent, right? X squared. So really, you could think of this as being written as A star B plus A. So if you write it out like that, which thing would you do last? Well, you do the plus last, right? So you would do this multiplication first. Actually, you do the exponent first, then you do the multiplication, and then you do the addition. Okay? So when you see this bar here, it's all the stuff on the left or all the stuff on the right.
Okay.
All right, so let's do the complete transformation from a regular expression to an NFA, then to a DFA. So step number one, we will do starting state. Got an A over here, and then B star here. All right, so all I did was I see there's a big OR in the middle, and so I have B star across the top and A on the bottom. Notice there's no loops at this point. All I've done is I've taken the piece on the left and made it its own transition, and took the piece on the right and made it its own transition. Okay, and then I'll take that B star and break it up into epsilon, B, epsilon. There's an epsilon looping back. There's one going all the way across. And then there's also an A here on the bottom. Let me, I got a little crammed up, so let me move it apart there. Okay, and that's my NFA. And then step number two, we'll use that same technique that I showed you at the very beginning of today, where we start here in, let's go ahead and label the states. This is 1, 2, 3, and 4. Okay, so if we enter into this, where do we actually end up if we enter in? If we enter in number 1, we could be in number 1, but we could also be in number 2, and we could also be in number 4. So when we enter in here, because of the epsilons, we could potentially end up in 3 states. So our starting state is 1, 2, and 4. Okay, so if we are in 1, 2, or 4, what transitions do we see? Well, we see an A here, and we see a B. The A would take us just to 4. And the B would take us out of 2 over to 3. And then because there's an epsilon, it could take us back to 2. And it could also take us forward to 4. Right? So if we start in 2, we end up in 3, or 2, or 4. So there's a B transition that takes us to 2, 3, 4. All right, so this 1, 2, 4 is done. We've fully explored both branches leading out. Let's do 4. 4 is also done because there's nothing leading out of it, so it's done. And then we'll do 2, 3, 4. So if we are in 2, 3, or 4, I only see a B leading out of there. So a B takes us to 3, and it also takes us back to 2, and it takes us forward to 4. So 2, 3, 4 on a B leads back to itself. And now this one is done. And then all I have to do is mark my final states. Anything with a 4 in it is a final state. So this one is a final, and this one is, and this one is. So you might recognize that picture. The names of the states are different, but it is identical to this one. Right? We did A or B star, and we ended up with this diagram. So there's a B followed by a loop or an A, and all three of them are acceptings. And so we ended up with the same thing. So we're able to end up with the same diagram, but we took a very step-by-step approach to arrive there. So we didn't have to do a whole lot of like thought and analysis along the way. Really, the only place where we had to expend a significant amount of energy was to figure out the order of operations. But once we got our Thompson's construction, we're able to just step-by-step follow the algorithm for converting the NFA to a DFA, and then we arrive at the same thing. Okay, so let's do this one, but now I'm going to show you how to use it with a table. So we're still going to start by doing Thompson's constructions. And did we already do this one as the constructions? We did. It's over here. Okay, I'm gonna just steal this. Let's number the states. 1, 2, 3, 4, and 5. Okay, NFA table. The table is going to be a little bit different than what we did before. We still have our symbols across the top, but we have a new column labeled epsilon star. And this column is going to be filled with what states can we go to if we follow 0 or more epsilon transitions. We could either follow no epsilons, or 1 or 2 or 3 or 4 of them, or as many as we want. Down the side, we're going to put our states. 1, 2, 3, 4, and 5. And let's fill this out quickly here. So in state number 1, it goes nowhere on an A and nowhere on a B. I don't see any, oops, let me back up. Sorry, if you're in state number 1 and you follow an A, you go to state number 5. I'm going to do that in red, actually. State number 5. If you are in state number 1 and you follow a B, doesn't go anywhere. And then finally, if you're in state number 1 and you follow no epsilons at all, you'll just stay in number 1. You can kind of imagine there's actually an epsilon pointing back to itself here. Okay, so if you're in state number 1 and you follow no epsilons, you'll be in state number 1. if you're in state number 1 and you follow 1 epsilon, you'll end up in 2 or 4. And then there's no way to follow 2 epsilons from there, so that's as far as we need to go. So if we're in state number 1 and we follow no epsilons, we'll be in 1. And if we follow 1 epsilon, we'll be in 2 or 4. So under here, we're going to put 1, 2, 4. That's what states we would be in if we start at 1 and follow 0 or more epsilons. Okay, 2a. So if we're in 2 and we follow an a, we'll end up in 3. If we're in 2 and we follow a b, don't go anywhere. And then 2, if we follow no epsilons, we'll be in 2. And if we follow 1 epsilon, well, we can't do that. There's no epsilons leading out of here. So we'll just be in 2. State number 3. Oh, go ahead.
What about the fact that 3 has an epsilon back to 2? So wouldn't the first one be 3 and 2?
No. So this is in state number 2 following just an A.
Okay.
So we'll worry about the epsilons later. The epsilons are handled by this column. Okay. So 2 following an A just simply goes to 3. Now 2 followed by an A followed by epsilons goes to other places, and we'll handle that later. All we're doing here is just trying to capture the information that's in here. Okay, 3A. See if we're in 3. There's no A's, so we'll just leave that blank. 3B. There's no B's, so we'll leave that blank. 3 on no epsilons is itself, so there's a 3 there. And then following 1 epsilon, we can go back to 2, and we can go to 4. So we've got 2, 3, 4 already. And then finally, are there more epsilons? There's not, right? So there's no way to go through further epsilons once we take these. So this is 2, 3, 4. Okay, state number 4A doesn't go anywhere. 4B goes to 5. And then 4 with no epsilons is 4. And that's it. There's no other epsilons coming out of it, so this is just 4. And then finally 5 on an A, nowhere, nowhere. And then 5 on 0 or more epsilons just takes us to 5. Okay, let's make our DFA table. So we're going to make this table a little bit differently. We're going to put A epsilon star up here at the top and B epsilon star at the top. Okay, so the way you make this top row is you take your two symbols and then you concatenate them with the epsilon stars. So these 3 columns became 2 columns in our DFA table. Oh, before I finish the NFA table, this is the starting and this is the accepting. So in our DFA table, the table itself is only filled with entries from the epsilon star column out of the NFA table. So these entries in here are only going to be ones out of this column up here. All these other entries here under the A and B are used as intermediate values, but are not actually used in the DFA table. Okay, so what is our starting state? So if we enter here at 1, what we're going to do is we're going to go all the way over to the epsilon star column, and whatever we see there is our actual starting state. So in our NFA, our starting is 1, but in our DFA, it's 1, 2, and 4. And the reason for that is if we go back and look at our diagram, if we enter into 1, we could stay in 1, or we could zip ahead to 2, or we could zip ahead to 4 because of those epsilons. So our actual starting state in the DFA table is whatever's under the epsilon star column for the starting row. So that's our start. Now, the way we're going to fill out this entry right here is we're going to look in the 1, 2, and 4 rows in the A column, okay, because we're doing the A's here. So 1, 2, and 4 in the A column. We're going to combine what we see there. So we have 3, 5, and nothing. So those combine together to make 3 and 5. Then we're going to look in the 3 and 5 rows and skip all the way over to the epsilon star column and combine what we see there. Okay, let me do that again. So we start at 1, 2, and 4 in the A column, combine what we see there, so it's 3 and 5. Then we look in the 3 and 5 rows and in the epsilon star column and combine what we see there. Okay, and that's what I mean by doing A and then epsilon star. We follow the A transition and see where that goes, and then we follow the epsilon star transitions and see where that goes. And that's equivalent to starting here in 1, 2, and 4 and following the A, which takes us to 3, or the A, which takes us to 5. All right, so if we're in 1, 2, or 4, we can take an A to 3, or we can take an A to 5. All right, so that's why we have 3 and 5. And then from there, where do the epsilons go? 1 goes to 2, 1 goes to 4, and you can also just stay in 3. Okay, so this is, what was it? Oh, 2, 3, 4, and 5. Do the same thing for the B. Start in 1, 2, and 4. Look in the B column. Combine what you see there, which is just 5. Go to the 5 row and look in the epsilon star column. And then whatever you see there is what you write here. Right? It seems complicated, but you're really just using this table as a, you're doing this lookup in this table twice. You're doing it once for the symbol and then once for the epsilon stars. So really it's just 2 array lookups. All right, I added 2 new things. I added 2, 3, 4, and 5, and just 5. Okay, so look in 2, 3, 4, and 5 in the A column. We're doing this right here. So that was combined to make just 3. Then look in the 3 row and the epsilon star column, and whatever you see there is what you write. 2, 3, 4. Okay, and then we'll do this one. 2, 3, 4, 5, B column. Combine those, and we get just 5. So now look in the 5 row and the epsilon star column, and whatever we see there.
Can you do the A epsilon star again for the 2, 3, 4, 5?
Okay, this one here.
Mm-hmm.
So look on 2, 3, 4, 5, A. Combine those values. So 3 plus nothing plus nothing plus nothing is just 3. Okay, and then go and look on the 3 row and the epsilon star column and combine what you see there. Just 2, 3, 4. So we did A followed by epsilon star. So we did a lookup to see where A goes, and then we did a lookup to see where E star goes. So again, if we look over at our diagram, if we're in 2, 3, 4, or 5, the A takes us to 3, and then the epsilons take us to 2, 4, or itself, which is 2, 3, 4. That's why we wrote that here. Okay, and then finally, we have, we added 2, 3, 4. So let's go ahead and add that to our table. Now we're going to do this one here. 5A, 5A, look up. Oh, nothing there. Then we'll do 5B. So 5B, do a lookup, nothing there. Didn't add anything new, so we'll move on to the next row. 2, 3, 4. So 2, 3, 4, A. Those combine together to make 3. So we'll look on 3, and then epsilon star, 2, 3, 4. And then 2, or we're doing this one here. 2, 3, 4, B combines to make 5. Go over to row 5. Epsilon star gives us 5. Didn't add anything new, so we're done with the table. So again, if you look over here, the only entries we have inside this table are entries from this row, or this column. We have the 2, 3, 4, 5 here because we combined this and this. We have the 2, 3, 4 because we combined that. 2, 3, 4 comes from there. And these 5s come from here. Oh, acceptings. Anything with a 5, right? This was circled over here. So anything with a 5. This one is accepting. This one's accepting. Okay, and then finally in our DFA, we've got 4 states. We've got state 1, 2, 4, which is our starting. 1, 2, 4 takes us to 2, 3, 4, 5 on an A. And on a B, takes us to just 5. 2, 3, 4, 5 on an A takes us to state 2, 3, 4. And state 2, 3, 4, 5 on a B takes us to 5. State 5 on an A doesn't go anywhere, and on a B doesn't go anywhere. And then finally 2, 3, 4 on an A goes to itself, and on a B goes to 5. And then this is an accepting, and this one's an accepting. Okay, so let's see. We've got 0 or more A's followed by a B. So we could do no A's followed by a B. So that takes us here. Good. We could do 1 A followed by a B. And we could do we could do several A's followed by a B. So if we do A, and then let's say 2 A's followed by a B, it takes us to here, and then 3 A's takes us this way, 4 A's, and then finally we could do just a single A here. Goes to our accepting up here. Okay. Got a little bit of time, so let's do this one. I guess no. Let's see. I don't want to do om nom. Yeah, let's do this one using the table. All right, we should end up with this, but let's try it. What was it? B star or A into DFA using tables. Okay, so first step is the NFA diagram, and we already did that. That is, where is it? No, not that one. No, not that one. This one. So I'm just gonna copy this. Save myself the trouble. Then we'll make our NFA table. Let's see, we've got an A and a B, an epsilon star column, and we've got states 1, 2, 3, and 4. This one's our starting, this one's our accepting. Okay, state number 1 on an A goes to 4. Right over here. State number 1 on a B doesn't go anywhere. And then state number 1 on 0 or more epsilons, we're in here. We can either stay on itself, we can go to 2, or we can go to 4. This is 1, 2, and 4. All right, 2A. 2A doesn't go anywhere. 2B goes to 3. And 2 on any number of epsilons just goes to itself. Three on an A doesn't go anywhere. 3 on a B also doesn't go anywhere. And then 3 on any number of epsilons goes to 2, goes to itself, goes to 4. And then 4 on an A and a B doesn't go anywhere. And then 4 on 0 or more epsilons goes to itself.
Professor, out of number 1, how come we have 2 A's coming out of number 1? I'm kind of confused because it's either B or A, like in other examples.
You're talking about
That's
this one
just
here?
a sloppy epsilon.
Oh, that's a sloppy epsilon, yeah.
Oh, epsilon, oh my god, that's what it was A.
Sorry.
Thank you.
Okay, for our starting state, we're going to look here in this row, but we're going to pull off whatever is under the epsilon star column. So our starting state is 1, 2, 4. That corresponds to coming into here and immediately going to 2 or 4 or staying at 1. Okay, so if you're in 1, 2, or 4, so you look in these rows, the A column, you combine what you see there, which is just 4. You then go to the 4 row and the epsilon star column, and you combine what you see there. And I see a 4. And then for the B's, for 4B, or 1, 2, 4B, we look on 1, 2, 4B. That combines to make a 3. So we look on the 3 row epsilon star column, and we combine what we see there, 2, 3, 4. So we just added 4 and 2, 3, 4 to our states. Okay, 4 on an A doesn't go anywhere, and B doesn't go anywhere. So that's taken care of. 2, 3, 4A. So we look at 2, 3, 4A. Combines together to make nothing. So we can put a dash there. And then 2, 3, 4B combines to make a 3. Then we go over to row 3, epsilon star column, and we write what we see there, which is 2, 3, 4. Okay. Didn't add anything new to our table, so we're done. Oh, I always forget. Mark our final. So anything with a 4 in it. Right, so we got a 4 circled over here. So anything with a 4 in it is accepting over here. All right, so finally, we'll just draw our diagram. We have a 1, 2, 4 state as our starting. That has an A that goes to 4 and a B that goes to 2, 3, 4. Four doesn't have anything coming out of it. And then 2, 3, 4 has a B going to 2, 3, 4. And then this is an accepting. Sorry, it's getting sloppy here. This is accepting and this is accepting. And notice that this diagram is exactly the same as, where is it? This diagram. So we just did it with a table instead of just doing it by looking at the state diagram. Okay, so that's the basics of how to do it. Now, if you're a computer, you'll skip the steps where you actually draw a picture. You'll go straight to a table. But once you have that in a table, it's basically just a two-dimensional array. You can fairly quickly do those lookups, and then you can combine what you see there fairly easily. You can just throw them into a set if you want to, and then you're basically just doing a union of all those different little sets. And then you generate your new table, and then from there you can execute it, right? Because this table then becomes something you can just run inside of an engine very quickly. So from our diagram, if we're a human doing this, then from here, or from here, we can basically write a program that would execute this state machine and would accept the same strings. So as I said earlier, if you look for online tutorials about Thompson's constructions, you'll end up with some slight differences. Primarily it has to do with these epsilons. So if you're doing a sequence here, then you just put epsilons on either end. They act kind of like train couplers, those little arms on trains that hook together. Again, you got the epsilons over here. And then for the UFO, you've got these epsilons on either end because it's the train couplers. And so the reason why you do that is because now you can do the A construction fairly easily. You can do the B star construction easily. And you can actually build those independently of each other. So you've got the A or B star. And then all you do is you hook them up with epsilons like this. Oops, that doesn't go that way. It goes the other way. And that's equivalent to putting in these over here. So you can go this way, and then go through this and then come back, or you can go this way. So notice that you end up with 1, 2, 3, 4, 5, 6, 7, 8 epsilons you have to deal with. So when you're transforming this into the tables, you end up with epsilons all over the place and lots of states. But still, eventually you will boil it down to just the same diagram you had before, just your state names are really big. So just be aware of that difference between the constructions that I'm using for this course versus ones you might find online.
Professor,
Mm-hmm.
what does it look like in like a programming language to like hook up the epsilons to different constructions?
Well, so NFAs cannot actually be written in a computer program. I mean, they can, but you actually have to do like brute force evaluation of it. So you want to go through this process where you eliminate the epsilons.
Okay.
Right? Non-deterministic finite state machines are not easily programmed. A deterministic one is easily programmed because you just have these if-elses. If I'm in state number 1 and I see an A, I go to this other state. But with a non-deterministic, if you see an A, you might go to one of 2 states or one of 3 states. And then you might have to do backtracking. You try the first one and see if that ultimately takes you to an accepting. And if it doesn't ultimately take you to one, you've got to back up and then try a different branch. And if that one doesn't take you to an accepting, you got to back up and try that third branch. So you end up doing a whole bunch of trial and error to try to end up at an accepting. But if you take the time to transform the whole thing into a DFA, then the program is very easy. So same thing with the epsilons. If you see epsilons in there, you'll want to go through the process of transforming it to a DFA so that you can then write a deterministic program that'll run it. Okay?
Mm-hmm.
So the epsilons wouldn't look like anything in your program because you would remove them. Okay. Well, that's actually all I had for you today. There's no assignment this week, for obvious reasons. So that pretty much wraps up regular expressions and finite state machines as far as evaluating our expressions. On Monday, when we come back from break, I will show you a different kind of finite state machine called a Mealy or a Moore machine. There are 2 different kinds, but they do the same thing. There's still state machines, but instead of producing either a true-false answer like these do, either you accept or you don't accept. Mealy and Moore machines produce a string of outputs. So you got a string of input, and you have a string of output. So basically, for every symbol in your input, there is one symbol for the output. So it's generating output as it goes. And it can do things like transform one string into another string in sort of a limited fashion. Right? So you can write a Mealy or a Moore machine. Those are 2 different kinds of machines. They could say, take a strings of 1s and 0s and invert it into a strings of 0s or 1s. So for every 0, you output a 1, and for every 1, you output a 0. All right, that's an easy transformation to do, but then you can do more complex ones, like you can actually do 2's complement entirely with one of these state machines, or you can add 2 binary numbers together using these state machines. So it's really kind of cool. So I'll take some time to show you those, and then probably on Wednesday we might do quantum computing, and then maybe for finals week we might meet and do some stuff. But really, I want to focus on meeting with each of you for about 5 minutes or so and just quickly go over all the work that you've done for the semester. So next week I'll also have a sign-up system in place where you can sign up for slots to meet with me. Okay? That's it. We're done. Have a great Thanksgiving.
Thank you, Professor.
Thanks.
Yeah, thank you. You too.
Thank you. It was great.
I had one last question,
Yeah.
Professor.
Yeah, what's up?
So for the deep dive assignments, we can turn them in late as well, right?
Yeah.
Okay.
Everything can be turned in late. Yeah.
Well, thank you. Have a good day.
You're welcome. Hey, I'm going to enjoy the weather. It's sunny, so get a little work done around the house, and then we'll start preparing for our big meal tomorrow.
I've had 100 things go wrong in the last week, so I'm repairing a ruptured dishwasher hose
Oh, no.
right now, so I don't get to go outside.
That's a bummer. Well, I hope you get it all resolved and that you're able to enjoy tomorrow.
Yeah, hopefully.
Yeah.
All right. Thanks.
See you next week.
Yeah, you too.
Bye-bye. All right, on YouTube, well, we didn't have very many people come and watch, but thanks for joining me. And I will see you also next week. I will not have a stream tomorrow. Tomorrow's a holiday for us. So no C programming tomorrow, but we'll be back on Monday, Tuesday, Wednesday, and Thursday next week. And then we'll see what happens the following week. Okay? So I'll wrap this up here. Have a good day, everyone, or night, depending upon where you are. And I'll see you next week. All right, bye-bye.